Welcome to the MOOCs course Advanced Thermodynamics. The title of this lecture is Liquid-Liquid Equilibrium Part 2. Before going into the details of today's lecture, we will be having a kind of recapitulation of what we have discussed in the previous lecture. In the previous lecture, we have discussed several aspects of thermodynamics of partially miscible systems, and then what are the conditions for the instability. Instability in the sense when we add two individual liquid solutions to make a kind of binary liquid mixture solution. Is that mixture is going to form a kind of single phase solution, or is it going to split into two phases? That is what we have discussed, and then conditions we have developed for those kind of partially miscible systems. Okay, what should be the condition if the system has to form partially miscible system? Those things we have seen, and then this lecture we will be discussing how to estimate the composition, equilibrium composition of liquid-liquid equilibrium problems. Okay. So, before going into the details of composition calculations of liquid-liquid equilibrium problem, we will have a kind of recapitulation of thermodynamics of partially miscible systems that we have discussed in the previous lecture. So, condition for instability of a binary liquid mixture we have developed as a dou square G mixture by dou x square at constant temperature pressure. If you obtain that one, that should be less than 0, right, or dou square delta mix G by dou x square at constant Tp, that should be less than 0. This is what we have seen, and then this equation, whether differentiation you do with respect to x1 or x2, it is same, it is holds for both of them. And then this one, this condition we obtained by taking Raoult's law as a kind of a reference state. Then whatever the GE expression is there for those kind of expressions, only we have developed this condition. That is, this Gibbs energy of liquid binary liquid solution is defined with respect to the Raoult's law. Under such conditions, then condition for instability is dou square G mixture by dou x square less than 0, or dou square delta mix G by dou x square is less than 0, provided the temperature and pressure are maintained constant. Then what is the this G of the system that we have seen? It nothing but G is equals to sigma xi Gi plus RT sigma xi ln xi plus GE. GE is nothing but molar excess Gibbs energy. Okay. And then if you take critical solution temperature or upper constituent temperature as Tc, then if temperature T is greater than Tc, or the system temperature or liquid binary liquid solution temperature is greater than this upper constituent temperature Tc, then mixture is completely miscible, because for all values of mole fractions, if T is maintained greater than Tc, we will be getting always this dou square del mix G by dou x square at constant temperature pressure is going to be greater than 0. This is what we are going to get, provided this temperature is greater than upper constituent temperature. Okay. So, if it is less than, then instability will be there, and then that will be forming a kind of a partially miscible two phases, right. So, obviously, in other words, if the temperature is less than Tc, less than if the system temperature is less than the upper constituent temperature, then mixture is partially miscible, because for some part of mole fraction range, what we will be getting? We will be getting dou square delta mix G by dou x square at constant temperature pressure is less than 0, which is the condition for the instability. Example 1. A mixture of benzene and isooctane system is described by GE is equals to x1 x2 multiplied by A plus B x1 minus x2 at 200 degree centigrade and 11.6 bar. Assume x1 is equals to 0.25, A is equals to 1616, B is equals to minus 122 joule per mole. Then question is it ever possible for benzene and isooctane to split into two partially miscible liquid phases? If so, under what range of temperature? That is the question. So, GE is given by this equation, which is nothing but 3 suffix Morgell's equation. If the GE of this particular system is described by 3 suffix Morgell's equation, under what range of temperature are we going to get two partially miscible liquid phases? That is the question. So, first what we have to find out? We have to find out dou square G by dou x square at constant temperature pressure, and then we have to find out the condition for T. If it is less than what, then it is going to form a kind of partially miscible system, that we have to find out. Straight and simple and straightforward. So, for splitting into two phases, we know that dou square G by dou x1 square less than 0, or dou square G by dou x2 square also can be less than 0. Then we can say that that solution will split in two phases, two partially miscible phases. And then G we have defined as sigma xi Ga plus RT sigma xi ln xi plus Ge. This is with respect to Raoult's law. This is with reference to the Raoult's law. Then this for a binary system of component 1 and 2, sigma xi Ga we can write x1 G1 plus x2 G2 plus RT sigma xi ln xi is nothing but RT x1 ln x1 plus x2 ln x2 for a binary system, and Ge is given by 3 suffix Morgul's equation, that is x1 x2 multiplied by a plus b x1 minus x2. Now, what we have to do, this equation we have to partially differentiate with respect to x1 2 times, then to dou square G by dou x1 square you get as RT multiplied by 1 by x1 plus 1 by x2 minus 2a minus 12b x1 plus 6b. This is what we get, dou square G by dou x1 square. Now, if the solution to split into phases or for instability, what we should have? We should have this one should be less than 0. That means, whatever this RT multiplied by 1 by x1 plus 1 by x2 should be less than 2a plus 12 b x1 minus 6b, or T should be less than this 2a plus 12 b x1 minus 6b divided by R 1 by x1 plus 1 by x2. This is what we get. Okay. So, if the system temperature T is less than the value, whatever this value is there, that is 2a plus 12b x1 minus 6b divided by R x1 divided by R 1 by x1 plus 1 by x2. This if you substitute the values of a, b, x1, x2 and R here, and then see what is the value of this right hand side is coming in of this inequality. Then if the temperature is less than that number, then we can say that under such range of temperature the solution is going to form a kind of partially miscible two phases. So, if you substitute A, B, R, x1, x2 in this above equation, then you will get T is less than 81.1 K. If the temperature of the system or mixing of this benzene and isooctane, if you do at a temperature less than 81.1 Kelvin, then you are going to have two partially miscible phases. They will not be completely miscible, that is what it means by. So, under this temperature range, benzene and isooctane will split into two phases, right. Then another example, example 2, Wilson equation requires positive values for binary parameters capital delta AB and capital delta BA. Verify that this activity coefficient model is incapable of describing the instability of partially miscible liquids. We have seen when we were discussing models for excess Gibbs energy for a binary and multi-component system, then we have seen this Wilson equation is not suitable for partially miscible liquids. This is what we have seen. Okay. So, that we can prove using this thermodynamics of a partially miscible system, whatever the conditions that we have derived. So, del square G by del x square if you do for this Wilson equation, then you will always get greater than 0. That is what mean by. If you are saying that it is not suitable for partially miscible liquids. That means you are not going to get the second derivative of G with respect to mole fraction less than 0 at any cost. Whatever may be the combination of capital delta AB, capital delta BA, x1, x2, R, T, and then whatever the combination of these parameters you take, you are not going to have this second derivative of G with respect to mole fraction as less than 0. If it is less than 0, then only that liquid solution is going to form partially miscible two phases or splitting into two phases. If it is greater than 0, it is always going to form a kind of completely miscible solution. So, that means when you use the Wilson equation and then do this derivation, then you will always find that this is going to be greater than 0. So, that is what we have to verify. Right. So, for the Wilson equation, whatever GE expression is there, that we have to write in place of G is equals to sigma xi GI plus RT sigma xi ln xi plus GE. In place of GE, you write the Wilson's equation and then do the second derivation of this G with respect to the mole fraction. Then you will find out for any combination of these parameters, this second derivative is going to be positive. It is always going to be positive. That is what you find out. Then it is correct, otherwise something is wrong, because it is known that Wilson equation is not suitable for partially miscible systems. So, obviously, the second derivative should always give greater than 0 for any combination of these parameters x1, x2, R, T, and then lambda AB, lambda BA, etc., those parameters. So, that we do. So, we know that GE is equals to GE plus sigma xi GI plus RT sigma xi ln xi. So, for a binary mixture of components A and B, G is equals to XA GA plus XB GB plus RT XA ln XA plus XB ln XB, and GE for Wilson equation is nothing but, or GE by RT for Wilson equation is nothing but minus XA ln of XA plus capital delta AB XB and then minus XB ln of XB plus capital delta BA XA. This is what we have seen Wilson equation for a binary system. So, in place of GE we can write minus RT of these two terms. So, that is what we are having here, minus RT multiplied by XA ln XA plus capital delta AB XB plus XB ln XB plus delta capital lambda BA. Then we have this term. When you substitute GE for Wilson equation, then we have this additional third term like this. Now, this equation, if you partially differentiate two times, so that to get dou square G by dou XA square, then if it is less than 0, then we can say that it is suitable for partially miscible system, that we have to check. So, first what we do, when we do this dou square G by dou XA square, then you will get RT multiplied by 1 minus XA minus 1 by XA plus capital lambda AB XB plus 1 by XB minus 1 by XB plus capital lambda BA XA. Now, we know this these two parameters, two adjustable parameters of Wilson equation, that is capital lambda AB, capital lambda BA, these parameters are always positive. So, now what you see, the numbers in this, whatever the combinations of XA, XB, capital lambda AB, capital lambda BA, if you take, whatever is the combination of these numbers including this R and T, you will never get this number as less than 0. You will never get this number as a negative one, because these parameters are positive, XA and XB are also positive, at the max they can be 0, and temperature is also cannot be negative, and then the R is also always positive constant, that we know. So, for whatever combination of these parameters you take, this is not going to be negative. So, this condition is not going to be satisfied. So, that means it is not suitable for partially miscible system. Since in Wilson equation these parameters are positive constants in RHS, the second term in parenthesis is always less than the first term, right. So, because of that one, this inequality, whatever the inequality criteria that we have shown here, that will never be satisfied, Thus, Wilson equation is incapable of describing instability of partially miscible liquids, or Wilson equation is not suitable for partially miscible liquid systems. That is what the conclusion, right. So, now using the principles of thermodynamics of partially miscible systems, you can check any model you can check whether that model is suitable for a partially miscible system or not. That is one you can check. Another one you can do for if it is suitable for partially miscible systems as well. So, under what conditions it is going to be suitable, those kind of thing you can estimate using the these principles of thermodynamics of partially miscible system, as we have done as 2 example problems, right. So, now what we do? We take up the next problem in LLE, that is estimation of composition of liquid-liquid equilibrium. Okay. We have already seen that when like interaction, whether AA interactions or BB interactions, like interactions in the sense same interaction or interaction between the same molecules, if they are very strong compared to the unlike interactions, then liquids can split into 2 different partially miscible phases. That is what we have seen. Obviously, if AA interactions are very strong, similarly BB interactions are very strong compared to the AB interactions. So, what will happen, rather they form as a kind of a completely miscible solution, they prefer to have a kind of pure AA solution, AA as a one phase, and then pure solution BB as a kind of another phase, but obviously pure will not be possible. So, there will be some amount of partial some amount of miscibility will be there, but complete miscibility will not be taking place as long as these like interaction, that is AA and BB interactions are going to be much stronger than this unlike interactions, AB interactions. So, if the like interactions are much stronger than the unlike interaction, then it is possible that these liquids are going to split into 2 different partially miscible phases, that we have already understood by this thermodynamics of partially miscible systems. Then these liquids form separate phases to lower the total Gibbs energy of the system. This is also we have seen why these 2 liquids, when we are adding together, they are forming 2 different separate phases as partially immiscible phases. Why? Because any system that will try to go towards the lower energy system, so that it can become stable. So, they will try to go towards a position where the system total Gibbs energy is getting lower. If the Gibbs energy is getting lower, so then system is going to be stable. So, in order to have a kind of stable, whether it is miscible solution or immiscible solution, the system wants to be at lower energy level. So, that is the reason the liquids forms 2 separate phases to lower the total Gibbs energy of the system. That is also we have seen. In this case, each species I tends to equilibrate between 2 phases, leading to liquid-liquid equilibrium. Okay. So, when we add these components, so component I tends to equilibrate between 2 phases, right. So, let us consider a binary mixture of species A and B. Then at equilibrium for component A, we know that Figasty of that component A in alpha phase should be equals to Figasty of component same A in beta phase. This is standard condition at equilibrium. Now, applying Lewis-Randall reference state, then this Fa alpha for a liquid phase alpha is what? Is nothing but Xa gamma A Fa naught for alpha phase. Similarly, Fa beta for beta phase is what? Xa gamma A Fa naught, but for beta phase. So, that is Xa alpha gamma A alpha Fa naught is equals to Xa beta gamma A beta Fa naught. This reference state is same for either of the phase. We cannot take 2 different reference states for 2 different phases which are coexisting. If they are individually existing, then fine, we can take different reference state, but if these two phases are coexisting and they are at equilibrium, then you cannot take two different reference states for the either of the phases. So, this FA naught for alpha and then FA naught for beta are going to be same. So, if you cancel out, this is what we have, that is XA alpha gamma A alpha is equals to XA beta gamma A beta. This is for component A. Similarly, for component B, if you write, then you will get XB alpha gamma B alpha is equals to XB beta gamma B beta. So, now if you have this information about the activity coefficient in either of the phases, then you can solve these two equations to get what is XA alpha and then XA beta. If XA alpha is known, then XB alpha is also known, because 1 minus XA alpha is nothing but XB alpha. Similarly, if XA beta is known, then XB beta is also known, because XB beta is nothing but 1 minus XA beta. So, these two equations, if you have this information about gamma A alpha, gamma B alpha, gamma A beta, gamma B beta, then you can solve to get this equilibrium composition. But it is not as straightforward, as easy as this equation looks like. Why? We will see with example problems. To know the activity coefficients, obviously we should have a GE model. Let us say if this system AB binary system, whatever we have taken, the activity coefficient are described by two suffix Margulis equations, then GE we have A x1 x2, and then we have seen for these equations ln gamma 1 or RT ln gamma 1 is nothing but A x2 square, that means gamma 1 is equals to A x2 square by RT under exponential, and then gamma 2 is exponential of A x1 square by RT. This is what we have. So, now that if you write for two phases, alpha and beta phases, and then component A and B, then for this equation is what? This is nothing but XA alpha gamma A alpha is equals to same XA but in beta phase, and then gamma A but in beta phase. So, that previous slide we have written that equation for gamma A alpha and then gamma A beta, we are writing this exponential of A xb alpha square by RT and then exponential of A xb beta square by RT, and then XA alpha and XA beta are as it is. Similarly, for component B also we have seen that xb alpha gamma B alpha is equals to xb beta gamma B beta, and then in place of gamma B alpha you can write exponential of A XA alpha square by RT, and in place of gamma B beta you can write exponential of A XA beta square by RT. This is what you can write, whereas XB alpha and then XB beta as it is, right. These are the two important equations. Now, another two important equations are XA alpha plus XB alpha is equals to 1. Though it is straightforward, it is very important equation, and in addition to this one, another equation XA beta plus XB beta is equals to 1. Though it is straightforward, this one also, these equations are going to be very essential. Why they are essential? Because whatever the solution that you get by solving these two nonlinear equations, this equation number 4 and 5 are highly nonlinear. You need to have a kind of trial and error approach, or some kind of numerical methods you apply to get these solutions. But when you try to find the solution for this equation, if that solution is not satisfying these equations, that means that solution is not reliable. That means that solution is not reliable. Now, this equation number 4 and 5 are nonlinear equations, and then these equations can be solved by trial and error approach or some kind of numerical methods. But if you see this equation, if you take XA alpha is equals to XA beta, any value of x a alpha you take, and then that you equate it to x a beta, then this equation would be satisfied. Now, x a alpha is equals to x a beta, so then these are same. So, exponential of whatever this x b alpha, if x a alpha is equals to x b alpha x a beta, then what does it mean? It means, so 1 minus x b alpha is equals to 1 minus x b beta. That means x b alpha is equals to x b beta. So, if x a alpha and then x a beta, if you take equals to each other, then whatever this x b alpha is there is equals to x b beta also, then this obviously this will also be equals to each other, then the equation is satisfied. Any combination of x a values you take, but provided if you take x a alpha is equals to x a beta. Now, again if x a alpha is equals to x a beta, then x b alpha is equals to x b beta that we have seen here, and then x a alpha you are saying that equals to x a beta. That means, any combination of x a values you take for two different phases are equal to each other. Let us say that is x a alpha, if you take equals to x a beta, that is in both alpha and beta phases the mole fraction of component A is equal. It is 0.1 or 0.9, 0.5, 0.44, whatever the number you take, if you take equals to each other, that is mole fraction of component A is equal in both the phases, then these two equations are always being satisfied. So, that means there could be n number of solutions are possible, but they are not reliable, because whatever the solution that you take, that solution should also satisfy these two equations, and then these two equations can be solved, and there will be only one solution which would be satisfying these two equations as well. Okay. So, that is the some kind of trivial solution is possible, that is if you take x a alpha is equals to x a beta, then any combination of this x a that you take in either of the phases, you get the solution, but that is not correct. That is not correct. So, that is the reason we have to do a trial and error solution, and then find out some values of x a alpha and then x a beta, which also satisfy this equation number 6 and 7. Not only just 4 and 5, they should also satisfy this equation number 6 and 7. Let us say we are going to see a few example problems as well, how to solve these equations. So, now equations 4 to 7 are set of 4 coupled equations that can be solved for 4 unknowns x a alpha, x a beta, x b alpha, x b beta, though there are 2 unknowns only, because 2 unknowns, remaining 2 unknowns are not independent for a binary system. So, but however, we have 4 equations, 4 unknowns we can obtain. So, similar approach can be used for GE models, other GE models also. Only thing that this equation GE in place of gamma A, gamma B, what are we writing, that expression will change, but the procedure is exactly same, but the procedure how to solve this equations is going to be same. So, let us take an example and then solve this equilibrium composition problem. Calculate the equilibrium composition of two liquid phases in a binary mixture of methyl diethylamine and water at 1 bar and 20 degree centigrade. The following 3 suffix Morgul's parameters have been obtained for the system. A and B are given. So, what we have to find out? We have to find out what is x a alpha, x a beta, and then x b alpha, x b beta you have to find out. Equilibrium composition you have to find out. So, at equilibrium we know for binary system A and B, we know that x a alpha, gamma A alpha is equals to x a beta, gamma A beta, and then for second component B also, we know that x b alpha, gamma B alpha is equals to x b beta, gamma B beta. This also we know. Now, if it is a 3 suffix Morgul's equation, then we have this RT ln gamma 1 is equals to A minus 3b x 2 square minus 4b x2 cube, and then for component 2 RTL and gamma 2 we have a minus 3b x1 square plus 4b x1 cube. This is what we have seen for 3 suffix Morgul's equation. So, similarly for gamma A, gamma B we can write for both the phases, alpha and beta phases. Then let us say for first equation for component A, if you write, this is exponential of a plus 3b by RT 1 minus xa alpha whole square minus 4b by RT 1 minus xa alpha whole cube is equals to xa beta as it is exponential of a plus 3b by RT 1 minus xa beta whole square minus 4b by RT 1 minus xa beta whole cube. Then similarly for component B, if you write, you will have this equation, right. This is for the gamma B alpha and this is for gamma B beta. This is gamma A alpha, this is gamma A beta, this is gamma B alpha, this is gamma B beta by applying 3 suffix Morgul's equation, right. So, now further we have this xa alpha plus xb alpha is equals to 1 and then xa beta plus xb beta is equals to 1. Now, here also if you take xa alpha is equals to xa beta, then we have 1 minus xb alpha is equals to 1 minus xb beta. So, that means this equation, if xa alpha is equals to xa beta, if you take whatever this parenthesis 1 minus xa alpha is nothing but xb alpha. So, xb alpha is equals to xb beta, that is what we get by taking this one, right. So, the first term is also same in the exponential, the second term is also same in the exponential, because xb alpha is equals to nothing but xb beta. Same is true for the second equation also. That means any combination of xa alpha is equals to xa beta, if you take, these equations are going to satisfy this equation 3 and 4, but this 5 and 6 may not be satisfied, right. So, that means what you have to do, you have to find out a kind of solution which is not trivial like this, which is reliable kind of solution. So, for that we have to do a kind of a appropriate trial and error approach has to be followed, or some kind of tools like MathCAD etc. one can use and then obtain the solution of these equations. So, alternatively following procedure can be followed for solving these equations. Make a guess for the value of xa alpha first, then solve equation 3 to get xa beta, that is this equation you solve to get xa beta, because now a, b, t etc. are given, only xa alpha and then xa beta are not known. So, you are making assumption of xa alpha and then finding out what is xa beta. Once xa beta is known, then you find out xb alpha using equation number 5, xb alpha is equals to nothing but 1 minus xa alpha. Then you compute equation 4 for getting the xb beta, this is equation number 4, this is 1 minus xa alpha is known, xa alpha is also known, xa alpha is known, 1 minus xa beta is nothing but xb beta, this is the unknown one, this you calculate, this you calculate equation number 4. Now, this xa beta also you already calculated from this equation number 3, this is also known. So, only thing is not known is xb beta. So, that xb beta you find out using this equation number 4. Then check whether this xa beta, whatever xa beta you found out and then xb beta you found out by solving this equation 3 and 4, are they satisfying this equation number 6, that xa beta plus xb beta is equals to 1 or not. If it is satisfied, then assumed guess of xa alpha is correct and then obtained values of xa beta, xb beta are correct. Otherwise, you have to make an assumption of another xa alpha and then continue this solution until this equation number 6 is satisfied, Okay. So, if the equation is satisfied, then the corresponding values of x A alpha, x B alpha, x A beta, x B beta are simultaneous solution to the equations 3 and 4, including that 5 and 6. And one should be careful that any trivial answer that x A alpha is equals to x A beta may be obtained if equation 6 is not satisfied, but obviously it is not the correct answer. Okay. But obviously it is not the correct answer. Okay. Difficult part of this computation is the solution of equations 3 and 4 for x A beta and then x B beta, because these equations are having some non-linear terms. So, now when you follow this solution step and then do some trial and error calculations, then you will find out answer to this question as x A alpha is equals to 0.855, x B alpha is equals to 0.145 and then x A beta is equals to 0.101, x B beta is equals to 0.899. There are other graphical approaches are also available for solving these equations. First, those graphical approaches, first what they give the range of mole fraction within which this solution is going to be there, right. The range of this x A alpha and then x A beta, that range first obtained by this approach. Then once finding the range, there is a kind of another graphical approach is there, by which you can find out exact solution of this x A alpha and then x A beta. So, those graphical methods I am not describing anyway, one can go through the books by Koretsky or Sandler, etc. Those books one can refer for these graphical methods. Now, we take another example problem. At 300 Kelvin and 1 bar, a binary mixture of species A and B form two partially miscible liquid phases. The following activity coefficients at infinite dilutions are reported, that is gamma infinity and gamma B infinity are provided. Using 3 suffix Margulis equation, determine the composition of two liquid phases in equilibrium. The problem is exactly same as the previous problem, but here these 3 suffix Margulis parameters A and B are not given. In the previous problem, these A and B parameters are given and then gamma A, gamma B for either of the phases you have to find out by trial and error approach until the solution satisfies that that equation number 6, that is x A beta plus x B beta is equals to 1. But now here these parameters are not given, but this gamma A infinity, gamma B infinity are given. So, here what we know that RT ln gamma 1 is equals to A plus 3B x 2 square minus 4B x 2 cube, and then RT ln gamma 2 is equals to A minus 3B x 1 square plus 4B x 1 cube for the 3 suffix Margulis equation we know. So, now first equation you substitute x 1 tends to 0, then that will be gamma 1 infinity. In the second equation, if you substitute x 2 tends to 0, then that will be giving gamma 2 infinity. So, gamma 1 infinity, gamma 2 infinity are given. So, you substitute those values here under these limiting conditions in both the equations, then you will be having two equations in terms of two unknowns A and B. If you solve those two equations, you will find out this A and B required for obtaining the equilibrium composition. Okay. A and B are not given, but gamma A infinity and gamma B infinity are given. So, first step is to finding out A and B parameters of 3 suffix Margulis equation. For 3 suffix Margulis equation, we know that RT ln gamma A is equals to A plus 3B x B square minus 4B x B cube. So, when x A tends to 0, that is if you take x A is equals to 0 in this above equation, then you get RT ln gamma A infinity is equals to A minus B, and then similarly RT ln gamma B we have for 3 suffix Margulis equation as A minus 3B x A square plus 4B x A cube. Now, if x B tends to 0, then RT ln gamma B infinity you will get it as A plus B. Now, this gamma A infinity and gamma B infinity are given. temperature is also given. So, if you solve these two equations, then you will have this A and B as 5990 joule per mole and 784 joule per mole respectively. So, now A and B have been found. So, then now you can find out the equilibrium composition by solving these two equations. X A alpha gamma A alpha is equals to X A beta gamma A beta, and then X B alpha gamma B alpha is equals to X B beta gamma B beta for 3 suffix Morgell's equation. For 3 suffix Morgell's equation, this is nothing but gamma A alpha, and this exponential of term is nothing but gamma A beta. Now, here this exponential term is nothing but gamma B alpha, and this exponential term is nothing but gamma B beta. In addition to this, we also have these two equations, X A alpha plus X B alpha is equals to 1, and then X A beta plus X B beta is equals to 1. So, now these equations 3 to 6, if you solve exactly similar way as we have done in a previous case, that is, first you assume X A alpha, then solve equation number 3 to get X A beta. Once X A beta is found, then equation number 5 you can find it out. Equation 5, you have X A alpha plus X B alpha is equals to 1, then you have X B alpha is equals to 1 minus X A alpha. So, now here X B alpha you are having. So, now you solve equation number 4 in order to get your X B beta. Here this is nothing but X B beta, right. So, once you have this X B beta by solving this equation number 4, then you take this equation number 6 for cross checking whether this X A beta plus X B beta, are you getting 1 or not. If it is coming, summation is coming close to 1, then this assumed X A alpha is correct, and then obtained X A beta and then X B beta are also correct. They are the solution. Otherwise, you have to make another assumption of X A alpha and then continue the series of calculations until you satisfy this condition of equation number 6. So, when you do several trial and error kind of solutions, then you will find it out. X A alpha is 0.85, X B alpha is 0.15, X A beta is equals to 0.18, X B beta is equals to 0.82. Now, we take one more last example problem to wind up this lecture. At 25 degrees centigrade and 1 bar, the following equilibrium composition has been reported to a LLE mixture of CHCl3 and water with X A alpha is equals to 0.987 and X A beta is equals to 0.0013. So, here equilibrium composition is given. Now, from these data what you have to find out? You have to find out these parameters A and B, 3 suffix Morgell's parameters A and B you have to find out. So, solution, these two are given, X A alpha is given. So, X B alpha is also known, 1 minus X A alpha is X B alpha, then X A beta is also given. So, that means X B beta is nothing but 1 minus X A beta. So, that is 0.9987. These 4 equilibrium composition values are given, and at equilibrium we know that X A alpha gamma A alpha is equals to X A beta gamma A beta. So, this one, since X A alphas the compositions are given. So, what we do, compositions we take one side, that is X A alpha by X A beta we take one side, another side we take gamma A beta by gamma A alpha, right. Then either sides we take ln. So, ln of X A alpha by X A beta is equals to ln of gamma A beta minus ln of gamma A alpha. This why we are writing? Because 3 suffix Morgell's equation, what is this gamma A gamma B we know, which are having these A B parameters, we can substitute here. So, they are the only unknowns, whereas the left hand side X A alpha X A beta are given. So, left hand side is known. So that this equation, after substituting these numbers, after substituting this gamma A expression for 3 suffix Morgell's equation, we can solve this equation. We need one more equation because we need to solve 2 unknowns A and B. So, similarly for B equation, for B component, if you write x b alpha gamma b alpha is equals to x b beta gamma b beta. Here also we take mole fraction terms one side. So, x b alpha by x b beta we take one side, another side we take gamma b beta by gamma b alpha, and then both sides we take ln. So, that we have ln of x b alpha by x b beta is equals to ln of gamma b beta minus gamma b alpha. Here also left hand side mole fraction terms are known. So, right hand side if you substitute 3 suffix Morgul's equation, whatever activity coefficient expressions are there for either of the phases, if you substitute, and then you get another equation. So, that is what we do. So, for 3 suffix Morgul's equation, we know RT ln gamma is equals to a plus 3b x b square minus 4b x b cube, and then RT ln gamma b is equals to a minus 3b x a square plus 4b x a cube, right. So, for alpha phase you write ln gamma a alpha is equals to a plus 3b x b alpha square minus 4b x b alpha cube by RT. Similarly, ln gamma b alpha is nothing but a minus 3b x a alpha square plus 4b x a alpha cube by RT. This is for the alpha phase. Now, for the beta phase, ln of gamma a beta is equals to a plus 3b x b beta square minus 4b x b beta cube by RT, and then ln of gamma b beta is equals to a minus 3b x a beta square plus 4b x a beta cube by RT. Now, if you do this equation number 1 minus 3 and then equation number 2 minus 4, then you will be having ln of gamma a alpha by gamma a beta, and then here ln of gamma b alpha by gamma b alpha by gamma b beta. So, these values are related to their mole fractions, right. So, they are equal to corresponding mole fractions. So, that if you have ln of gamma a beta minus ln of gamma a alpha is equals to this term, which is nothing but ln of x a alpha by x a beta. We have already done previous slide simplification. So, here this x a alpha x a beta are given. So, R T are known, and then here x b alpha x b beta are also known. So, except a and b everything is known in the parenthesis. Similarly, for we have ln gamma beta, ln of gamma b beta minus ln of gamma b alpha, then we have this expression, that is nothing but ln of x b alpha by x b beta, right. What we have seen in the first slide, we have seen first slide of this problem, ln of x a alpha by x a beta is nothing but ln of gamma a beta minus ln of gamma a alpha. This is what we have seen. So, what we have ln gamma a beta, so this term, and then ln of gamma a alpha, this term. So, this this is equals to ln of x a alpha by x a beta, this is known. So, that we have substituted. Similarly, other case what we had this expression ln of x b alpha divided by x b beta is nothing but ln of gamma b beta minus ln of gamma b a. So, this is nothing but ln of gamma b beta, and this is nothing but ln of gamma b alpha is equals to ln of x b alpha by x b beta, these are known. So, this now you substitute except a and b everything is known in this equation also. So, now equation 5 and 6 are two equations in two unknowns a and b. So, if you solve these two equations 5 and 6, then you will get a is equals to 13,700 joule per mole and b is equals to minus 2798.5 joule per mole. So, this is how the equations associated with the liquid-liquid equilibrium can be utilized to find out not only the equilibrium composition, but also to find out the parameters associated with the different GE models applied or used for describing the non-ideality of the liquid phases. So, with this we complete the discussion on liquid-liquid equilibrium as well. The references for this lecture are given here: Engineering and Chemical Thermodynamics by Koretsky, then Molecular Thermodynamics of Fluid Phase Equilibrium by Prausnitz et al., and then Chemical, Biochemical and Engineering Thermodynamics by Sandler et al., and Introduction to Chemical Engineering Thermodynamics by Smith et al. Thank you.